So I had a student or two email me about questions of this type, which is a word problem. And in this word problem, they're telling you that they're going to create a box from a 6 centimeter by 6 centimeter piece of cardboard. They're going to cut an equal amount off of each corner. So these little square corners are going to cut out. And they're going to fold all these flaps up to make this open box with no top. And so with this information, they want us to find an equation that gives us the volume. Once we find an equation that gives us the volume of this box that we create, it wants us to tell them what the domain is. And then further down in the problem, they give us a graph and ask us to answer something about this box that we're theoretically creating as well. So they tell us that originally, before we started cutting pieces away, that this entire length here was 6 centimeters. And same here from all the way from top to the bottom, 6 centimeters. And here, here, and here. So it was a square piece, 6 by 6. And then they cut away this little piece X from it on every corner. And so if we think about volume, volume is of course length times width times height. And so this box that we're creating, this little piece here, do it in a different color, that might help a little. This piece here that's going to be one of my sides of my box, so this in here, it was created by originally having 6 centimeters, but then some number of centimeters X was cut off on either side, which means I cut off 2X in total from this little side that was originally 6 centimeters long. Which means this side now is represented by 6 minus 2x. And the same thing is going to happen here, because again, originally my piece of cardboard was 6 centimeters from top to bottom. I cut off an x at the top and an x at the bottom, which means this flap here that we've created for our box is also going to be given to us by 6 minus 2x, whatever x happens to be. So I'm going to have a length of 6 minus 2x. I'm going to have a width of 6 minus 2x, which means this is going to be a square box with an open top, kind of like a puzzle box maybe. And it's going to have a height of x, because if that's what I'm cutting away, when I fold it up, because that's what this little length is right here, when I fold it up, this piece is going to come x units high. So for our volume, we're going to have a length of 6 minus 2x. We're going to have a width also of 6 minus 2x, and we're going to have a height of x. And so if they wanted in factored form, we could do this. Generally with factored form, we tend to put the x in front, and then this factor is used twice, so we would write 6 minus 2x, and then we'd have that squared quantity on the outside. So this is our volume function of x. And this will tell me what the volume is going to be for this box, depending on how much I cut out of the box. So if I cut half a centimeter off, I'd put 0.5 in here, 0.5 here, and when I went through the calculations, it would tell me what the volume was going to be for this box that I've created. So that's part of our answer. From there, the question then asks us to find the domain of this volume function. So if we want the domain of the volume function, even though this equation all by itself does come out to be a polynomial, and polynomials do have domains of all real numbers, this particular function doesn't get to act like every other polynomial because it's bound by the reality of the situation. And so the reality of the situation is that if I have a 6 centimeter piece of box, or a 6 by 6 centimeter piece of cardboard that I'm trying to cut away from to create this box, well, then I can't cut away a negative quantity, right? I can't cut out negative 5 centimeters from this piece of cardboard. So I have to have something that is bigger than 0, because I also can't cut nothing away, because then I can't fold up this box. So my domain can be close to 0. I can cut away 0.0001 centimeters of that box and still be able to create a box theoretically. And it can go up, but it doesn't get to go up to infinity because again, we're only working with a 6 by 6 piece of cardboard, since really none of these factors get to be 0, because if they're 0, I'm not able to create a box. So that's why here we didn't get to include the 0 because of this factor. And then this factor is going to bound it for me on the top. So 6 minus 2x, I don't want this to equal 0 either. If I plug in a value of 3 for x, that would give me 6 minus 6, which would give me 0, which means I can get really close to 3, but I can't have it actually equaling 3. So that means my domain here is going to have to be from 0 to 3, because anything outside of this set of values is either going to be not possible because we can't cut away a negative quantity, or I would be cutting away more than I actually have to give. So if I tried to cut away, say, 4 centimeters from each side, well, 4 centimeters here and 4 centimeters here would give me 8 centimeters total, and I don't have 8 centimeters to work with, I only have 6 centimeters to work with. So that's the next part of the question they asked us. And then lastly they say, okay, well, if we know that this is our domain function, if we give you a graph of our domain, which they then give you, so this is given in the question, they say, if we give you this graph, can you tell us what the dimensions have to be to yield a maximum volume? So there's more to this graph, but they don't give it to us because we don't care about what happens outside of that 0 to 3 domain, because that's not a reality for us. So for this piece of the function that they give me, I do have a relative maximum, and if I have a relative maximum, that means this is the biggest volume I'm going to possibly be able to get out of this box that I'm creating for the situation that they wrote for me in the problem. And that maximum is occurring at the point 116, which means x is equal to 1 centimeter. And when x equals 1 centimeter, it's going to spit out for me a volume of 16 centimeters cubed is what that means. And so we know that we can cut away 1 centimeter, and they want to know, if we're cutting away 1 centimeter, what does that mean that the length, width, and height of the box that we're creating going to be? And so if we go back to what we did way over here, we said our length was going to be given to us by the expression 6 minus 2x. Our width was going to be given to us again by 6 minus 2x. And the height of our box was going to be given to us by x. Well, according to the graph of this volume function, the max is occurring at a volume x equal to 1, So I'm going to go through and plug in 1 for x on all of these and see what I get. So 6 minus 2 times 1 would give me 6 minus 2, so 4 centimeters. The same exact thing is going to happen here because the expression is exactly the same. So I have a length of 4 centimeters, a width of 4 centimeters, and a height of only 1 centimeter. And these dimensions of 4 by 4 by 1 box are what's going to give me the highest volume for the box that I'm creating in this situation. I hope that helps. Thank you.